Yeah, so we're jumping now into the next presentation, which is HTPK as a bridge to early development. And as I mentioned earlier, I'm Eric Jamois, Director of Business Development at Simulations Plus. So the first part uh, of this session is going to be sort of a brief slide overview of the HTPK technology, and then I will hand it over um, to David, who spoke previously, and he will take over and give an overview of the software live. So, so what is the first thing I'd like to share with you is the kind of vision that we had in putting this technology together, and so how we envision a high throughput PK calculation would actually work. Um, and So we developed this as a simplified early PK assessment tool for non-DMPK experts. And so the idea is to provide dose and time-dependent modeling capabilities, also to avoid the need to provide experimental values, at least initially, but then allow the use of experimental values later on if they become available. And of course that is in the spirit of identifying potential development issues as early as possible, if even before compounds are synthesized. So as David mentioned earlier, this is the technology was initially developed in-house, and then we got a lot of interest from one of our large pharma partners who was very interested in furthering the development of this technology. And there were actually two phases of development. One, the first phase that started in April last year, um, and um, and then another one which started about 6 months or so after that, and continued until just a couple of weeks ago. And we, as of February 28, delivered the last improvements that we made to the technology. So again, there's been a lot of R&D work that's been invested in providing these capabilities in the ADMET Predictor platform. And of course, we have a certain vision of all the uh, all the properties that can be computed in terms of CP time curves, for example. Let me just turn on my pointer here. Um, CP time curves that can be obtained, and also a parameter sensitivity analysis that can be done. But our clients also have their own vision, of course, of how they want to deploy it. And certainly that is a tool that can be deployed by through other front ends. For example, we have some of our clients deploying this technology through the Spotfire interface, which is what you can see here. So, I mean, in general, technologies that come from us are deployed in a multiple number of ways. It can be through command line, it can be through Pipeline Pilot, KNIME, general workflow tools. So again, there's many ways that it can actually be deployed. So this technology, as I think David mentioned earlier, is taken from initially from GastroPlus, and uses the so-called ACAT, the advanced compartmental absorption and transit model from GastroPlus. So essentially, it elaborates this fairly complex system and solves a set of differential equations that are associated to that system. So it's a very different kind of modeling. This sort of mechanistic modeling is very different from what Bob just talked about in terms of statistical models. So and so there are a number of things that we simulate that are directly from the GastroPlus implementation. There's also a number of simplifications that we introduce to make these calculations fast. For example, gut clearance is not considered. We only use passive absorption kinetics, although the paracellular phenomenon are included. Clearance is assumed to follow linear kinetics. Antero hepatic circulation and biliary excretion are not considered. First order precipitation kinetics is assumed. Right now, the only dosage form is IR tablet, although IV bolus will be available in the next release. And the physiology is limited to fasted adult human or rat. Um, so, but that's still, with that, is quite a wealth of capabilities. So what sort of, again, parameters do we have access to through this technology? So of course we have access to fraction absorbed, that's percent FA, fraction bioavailable, percent FB, Cmax, Tmax, AUC, T1 half. This is something that can be computed as David already showed fairly quickly on a set of compounds. You can also generate CP time curves, now supporting multi-dosing. You can do parameter sensitivity analysis, and you can also back calculate the dose that would be required to achieve a certain target plasma concentration at steady state. And that can be different for every compound. Of course, you can actually feed that data through a separate column and have it be different for every single compound as a function of their activity. And then also provide access to the ECCS major clearance mechanism. So a lot of capabilities. And so this is like a couple snapshots of the interface, where you can select your species, rat or human. You can select your doses. You can, of course, have multiple doses, and that's one of the beauties of this technology. You can actually run the calculation with multiple doses and see, for which compounds percent FA is dose dependent and for which ones it's not, for example. And same thing for bioavailable fraction. So you can input your clearance model, etc. So you have access to all of these options. And then also behind the scenes, you actually have two ways to proceed. You can perform the calculation exclusively in silico, where there's really nothing else that's required besides the structure. But again, as you advance in a particular set of compounds and you have experimental data that becomes available to you, you can actually provide these experimental values to make the simulation more accurate. So so all of these parameters that can be calculated in the backend, if you don't have them, then again you can input specific experimental values for. So we did a couple, actually several validations of the technology. Some involved experimental data, some involved direct comparison with GastroPlus. This slide, I only have a fairly limited amount of time, so I'm only showing you what we did in comparison with GastroPlus in, of course, an apples to apples setting. And on 100 compounds, these were approved drugs. The time to run this in GastroPlus was a few minutes. The time in Admit Predictor would be under 1 second. So it's extremely fast technology, and again, to the point that, of course, back to the spirit that these tools can be used very efficiently in a discovery setting. So these are actually some benchmark timings for percent FA and percent FB in human after 24 hours. For 3 different dose levels, I actually run that calculation on the enamine diversity set of over 10,000 compounds. With the previous version of the software, it took 7.5 minutes. With the current version, it took 1 minute and 30 seconds. So that's 117 compounds per second. This is a multi-threaded, like all the other properties in the software. It's multi-threaded calculations, and I was running this locally on my laptop. So gives you a sense of what you can do. On the R&D horizon, as I said, it's an area that's been extremely active for us in terms of R&D. The IV bolus route of administration will be the next release. The ability to define non-specific binding. the ability to define free target concentration, supporting the use of CTROF of a Cmax use in dose optimization, and then other enhancements to the use of .inp and .hia files as part of the input. I want to make an announcement of a webinar that will be given dedicated to the technology, and it will actually be given by Andres Olivares, who is a project leader at Roche in the clinical pharmacology team. And again, he will talk to us on April 21st on, again, early assessment of PK properties using ADMET Predictor HTPK simulation technology, and give us a sense of how it is being deployed at Roche. So we look forward to his presentation. And in the meantime, I thank you for your attention, and I'm passing the baton to David for a demo of the technology. Thank you.
Okay, thank you, Eric. Am I still unmuted?
Yep, I think you're good. Yep.
All
I'm
right.
gonna stop my video, and I'm gonna.
Okay. So thanks for that introduction. I just wanted to point out, while it's on my mind, that I know you didn't have a chance to show some of the validation versus experimental, fraction absorbed and fraction bioavailable. But again, on our website, we do have links to the webinars that we've given. I think we've given probably 2 or 3 on HTPK. So there's information there to fill in a little bit more background. So I'm going to do a little demo of some of the features that we've added as part of this ongoing collaboration. Some of the improvements, I would say, are pretty advanced. These are advanced users. It's been a great collaboration. I would say we've learned a lot. We're excited about the improvements. They're a little difficult, I think, to explain some of them in this short time frame. So I'm going to focus on some of the more basic ones. I'm going to use as a sample set, as my demo set, 1,000 FDA drugs. So I'm going to load that SD file into ADMET Predictor. Hopefully you caught the earlier talk. There's a lot of really nice functionality in ADMET Predictor, not just the HTPK, but a lot of other great features. Let's see, to give a relative sense of the speed, I'll start by predicting all of our ADMET properties. I'll include all of the categories: phys chem, transporters, metabolism, and I'll include the full set of molecular and atomic descriptors. Eric alluded to the parallelization that we recently added. So on this set, it's very fast. Results, of course, in a set of prediction columns. These graphical star plots are optional. I talked about much of this at 8 o'clock Pacific this morning. Okay, so now I'm going to run the HTPK simulation. Eric just showed this user interface. So I'm going to select human, immediate release tablet. Eric alluded to the new IV bolus option. So I am, by the way, running the pre-release version of ADMET Predictor, version 10.2, and we are planning a new release. We're targeting the April-May timeframe that will have all this new functionality in it. Leave the choice of 1 milligram as the dose. Eric explained again that the other parameters like clearance and then those on the advanced dialog are all ADMET Predictor predictions by default, and those can all be overridden with experimental data if you have it, or with models that you've built yourself. You can enter numbers here or fields from an input file. And this all works both from the user interface and from the command line. The command line, of course, also works on Linux. So if I launch that, The prediction speed is on the same order of magnitude as for the ADMET property generation. So it's quite fast. And again, you get a series of result columns like fraction absorbed, fraction bioavailable, and a number of PK parameters. Just going to scroll out here. One of the things we added as part of the collaboration was to provide an estimate of the AUC, the area under the curve, from 0 to infinity. It's an important pharmacokinetic parameter. Just briefly show that if I sort on that attribute, you'll see that it's missing for some of the compounds, maybe just a handful. If I quickly generate a CP time curve for one of those compounds, just using the same parameters, you'll show this kind of curve. You see that Cmax is never achieved in that 24-hour time frame. That's the default dose interval. That can be changed, but you see that the curve never starts to descend. So it's impossible to provide a reliable estimate for AUC 0 to infinity. Now, it turns out that both the clearance value and the half-life are defined using the AUC 0 to infinity estimate. Clearance is proportional. I'll show the tooltip here. Proportional to dose over AUC and the half-life to volume of distribution over clearance. So both of those values are also missing for these compounds. I wanted to mention that it turns out that our GastroPlus software provides a half-life estimate using a different clearance value, namely the scaled plasma clearance defined using the well-stirred model equation. We do output that clearance as well. So you can use an equation in Predictor to define that theoretical half-life that's the same as the one that you would see in GastroPlus. We also have a feature to tell Predictor to compute a set of user-defined equations automatically each time an HTPK simulation is performed. So just briefly to illustrate that, I think this is a nice feature. It's turned off by default, but if I turn it on, and I'll just do it for a handful of these compounds. Now, if I rerun that simulation on just the selected row, you'll see that it adds a new column. So this would be what you might call a theoretical t-half based on the well-stirred model clearance, and should match the value that you would see in the GastroPlus interface. Okay. As Eric mentioned, several of the recent improvements were to the dose optimization feature. So I want to give just a basic overview of that feature. I'm going to choose just a single compound. I'm going to choose the drug alprazolam. It's the compound I was showing earlier this morning. So I'll find that compound, and then I'm just going to hide everything else. Let's see, hide. I'll make this a little bigger so you can see it. Okay, now you'll recall that the dose optimization feature is used to estimate the dose required to achieve a target total plasma concentration at steady state. So I'm going to start by generating a CP time profile for this compound that runs out to steady state. So I'll launch that CP time feature, leave the default options, but I'm going to specify 3 dose intervals. So that means 1 dose given every, in this case, 24 hours. You can change that 24. So if I run that, I get a curve like this. So the first thing you see is that it does, seem to at least approximately reach steady state. The Cmax and the Cmin are not changing with the 3rd dose. Now, the average plasma concentration at steady state is defined as the steady state AUC divided by the dose interval of 24 hours. the legend here, like the spreadsheet, shows the steady state AUC. And here you can actually see that it's the same as the estimated AUC 0 to infinity, which is what you would expect in the linear pharmacokinetics regime. So back in Predictor, I can create an equation to define the average total plasma concentration at steady state. So I'll do that by, let's see, saying add compound attributes equation. I'll call it C target in nanograms per milliliter. And I'll use the AUC 0 to infinity estimate, which we already have in the spreadsheet, divided by 24. Okay, and I get an average total target plasma concentration of 1.97 nanograms per milliliter. So now if I were to run the dose optimization feature and say that I want my target, again, average total plasma concentration to be that value I just calculated. I could type 1.97 here or use the attribute that I just added to the spreadsheet and run it. I should, and I do, get an optimal dose of exactly 1 milligram. We expect that because that's the dose that we used originally in the simulation to get the AUC, which was then used to, derive the average plasma concentration. Now, if I run that again, and this time specify, whoops, I'm going to run optimal dose again, and this time specify that rather than C average, I want that target concentration to be the minimum total plasma target concentration. I get a different optimal dose. So now it's larger, it's 2.9. So if I were to take that dose and generate a CP time curve, here I'll just type in 2.9. I'll still run it for 3 intervals. So now it still appears to achieve steady state. And you see that at steady state, the C min, now the trough here, is exactly what we were requesting. It's about 1.97 nanograms per milliliter. Okay, so obviously that is not a validation of the dose optimization feature. It's an internal self-consistency check. But hopefully that has helped to illustrate how the tool works and given you some idea of how it might be used. Okay. Another set of improvements that we made was to the feature for estimating concentration time profiles. In particular, making it easier to visualize the effects of parameter changes. So I'm going to illustrate that using our companion MedChem Designer sketch tool. So I'll send this compound over to Designer. This tool has a lot of functionality. You can predict ADMET properties directly. This is very useful for, experimenting with structural changes and then getting immediate feedback as to the effect on all of the predicted properties. You can also predict metabolites. I showed this in the first seminar this morning. Designer also incorporates the HTPK functionality, including the feature for estimating CP time curves. So if I go back to alprazolam and generate a default curve, I'll go back to 1 milligram and just one dose interval. You would get a curve that looks like that. But now if I'm interested in directly comparing to an IV bolus simulation, I could just rerun, change the parameter again to this new option. And then instead of a new window, just say attach to the existing one that I've already generated. And then now you can see a direct comparison between the oral and the IV dose. You could experiment with changing some of the other inputs, for example. So if I launch it again, I'll go back to the IR tablet. If I launch the advanced tab, there's an option to load previously calculated ADMET property predictions directly into the dialog as numbers. so that you can see them more quantitatively. So for example, if I took solubility and increased it to 0.03 milligrams per milliliter to see the effect on the simulated CP time. Again, so this is the default oral dosing, and then this is the result of a pretty significant increase to the solubility. So you see a large increase in the Cmax. Another feature was being able to handle multiple compounds simultaneously in the CP time feature. So since we're in Designer, you can just make a copy, make a structure change, like so, and then get a prediction for both of the compounds together, like that. So this is the original structure, alprazolam, and then this is the modified one. This is a pretty good match to experiment, as it turns out. This one I actually have no idea. Okay. Lot of other functionality, as I said. Some of it, was a little bit more on the advanced side. These collaborators are quite advanced, and they're making just tremendous use of the software. Not always the user interface. Some of it is driven by the command line. So we have, made sure that the command line version of ADMET Predictor, really has all of the capabilities, at least as far as the HTPK module goes. That the user interface has. And that, as Eric mentioned, they are primarily using it to power a different user interface. Okay, we're at about 28 past. I think I'll stop here and hand it back over to Eric for any questions that we might have.
So there were a couple questions that came in the chat window. And I actually answered them by text, but maybe we'll. I don't know if everybody's able to see them or if it's just the people who asked the questions who can see them. So there was one relating to how HTPK differed from GastroPlus in terms if it was just kind of like a batch version of GastroPlus, and what's the difference. I think the key differences are that number one, there are a lot more physiologies and options that are available in GastroPlus. So it's on the GastroPlus side. And on the ADMET Predictor side, HTPK, of course, a very significant speed advantage, probably in the range of, as I put on the slide, probably about 2 orders of magnitude or so, faster. I don't know if we have more precise benchmark, but I did have one on my slide. So.
Yeah, I should maybe point out that there's an ongoing effort to sort of modernize GastroPlus. It's being converted to C++. I think after that's completed, you probably could expect roughly similar performance between ADMET Predictor and GastroPlus. I think you had a nice slide that sort of summarized some of the differences between AP and Gastro. Things like not being able to specify a KM and Vmax, in terms of the clearance. You're limited to using an intrinsic clearance value in Predictor. There's a few, simplifications like that. Again, it's geared towards non-DMPK experts. And of course, HTPK does not have all the other modules that Gastro has, the DDI module and other routes of delivery, ocular and, pulmonary and things like that. So it's meant to be more limited to early discovery scientists.
Great. Thank you for a great answer, David. All right, so I think I'm going to close this session here.